So this will be a nice review of things you already know. So we won't spend too much time on this and have a little bit of time at the end of the class. Hopefully you get some things done. But we spent a bunch of time on looking at these functions that were geometric series that started at 1, so they had x minus 1. Then we looked at how to get to them not having a minus 1, and now we have arrived to exponential functions. So these are going to be connected. They're not going to be just dots anymore. It's going to actually be a whole line connecting everything. And realize it's a exponential equivalent of mx plus b. All right? They both have the same things. They both have a starting place, which when you're graphing a straight line is b. That's the y-intercept. On here, it's going to be a. You always start at a. That's the y-intercept. So one's a, one's b, but they're the same thing. That's where you start. On a straight line, this slope, if it's less than 0, I should say, if it's less than 0, it's going to be negative and opening down. If it's greater than 0, right, it's going to be positive slope going up. It's kind of like that for B. B is the thing that tells you is it going up or going down, but instead of 0 being the division point, it's at 1. So greater than 1, that's when it's growing, exponential growth. And if it's less than 1, that's when it's going down, decay. So very similar to the y equals mx plus b, just adjust a little bit for instead of above and below 0 is negative and positive, it's now above and below 1 is increasing, decreasing. Okay. So 1, of course, if you multiply by 1, you go nowhere. 1.1 makes it go up. If you multiply by 0.8 or something, that's going down because that's like 80% of what you had prior. It's less than what you started with. All right, so keep that in mind. They're one and the same, right? So let's start graphing a little bit and look at this. So if we're going to graph y equals 2 to the x, you just have to plug in some values. Good way to do graphs from the very beginning is just to do good old-fashioned t-chart and plug in a bunch of values and see what they equal, and then just plot the points. So we're going to find 2 to each of these powers, right? And then simplify each one of them. So 2 to the third is 8, and 2 to the second is, and 2 to the first is, and 2 to the 0 is, and 2 to the negative 1 is. So follow the pattern. Divide by 2. Divide by 2. Divide by 2. 1 divided by 2 is 1 over 2. 1 divided by 2. Divide a half by 2, you get a quarter, right? So another little Algebra 1 concept, that negative exponents equal positive small numbers, right? These are not negative answers. These are all positive fractions. So we use negative exponents not for negative numbers, but for very, very small positive numbers. So in your science classes, you often use scientific notation. That might be like 6.28 times 10 to the negative 17, like for something microscopic. This just means 17 zeros and then 628. It's still positive, though. It's a very small positive number, microscopic or atomic size, but it's a positive number. This whole thing is positive, just like to the negative power are positive. So we got to keep that in mind moving forward. And then let's plot all those points. Just plot those on the graph and connect them with a nice smooth curve. Okay, so we have quarter, half, 1, 2, 4, 8, and there's even room for 16. And you'll notice we have a nice smooth curve. Okay, just like that. Oh. All right, and then all the typical questions that come along with graphs. What's the domain? What's the range? What happens if x gets to positive infinity, negative infinity? Any asymptotes, any intercepts, and its concavity, up or down. So, start with the domain. What is the domain? Yeah. So, what's the furthest to the left and furthest to the right we can go with this graph? And then you would say? Can we keep going forever here? Yep. So we can go to negative infinity. What about the right-hand side? Can we keep going to the right forever? Yep. So that's all real numbers. No longer are we doing 1, 2, 3, 4, just positives. Right now we can have negatives, and these are connected, so not a sequence anymore. So we can have a full domain. What about range? What is the lowest point of this graph? 0, right? So 0 is the lowest point. And you should also note that as x approaches negative infinity, the y's approach 0. And we can never actually equal 0 here, because there's no number I can plug in for x that will give me an answer of 0. Even the smallest negative number, negative 1 billion, I plug that in, 2 to the negative 1 billion, it's still a positive number. It's not 0. Very close to 0, but it'll never actually be 0. So for that reason, it's a parenthesis, not a bracket. And we have, let's see here. What is the highest value, highest y value we can have? We go to infinity. All right, so that's what happens when we increase, as x goes to infinity, the y values go to infinity. The asymptote is, we kind of talked about it, something we can get close to but never actually equal. 0. All right, y equals 0. And since it is an asymptote, that is why, once again, this is a parenthesis, not a bracket, because asymptotes you can never actually equal. So all the color coding here is actually for a reason, and like these two values are the same as these. Since this is an asymptote, that's why 0 is not included. So nice little review built in here. Intercepts, no x-intercepts because we can't hit the y-axis here, or the x-axis, y values. But we do have right here a y-intercept, so we have, that's also from here, where the x equals 0, that's called a y-intercept. So we get 1. 1. And its concavity is going up, going up. Okay. So that's just a little review from Algebra 2 on just graphing exponential functions and looking at all the little characteristics. Okay, so in order for it to be a true exponential function, it has to have that format where you have A, which is where we're going to start, B, which is how much it's growing or decaying, and it has to have a variable exponent. It has to have those three things. Okay? So on A, does it have all three things? I mean, we have a B, because that's what's being raised to the x power. We have the x. Is there a number in front? Or could we infer a number in front? Yeah, we could always just put a 1 times that. So when you were graphing straight lines, if you had a straight line that was y equals 2x, they didn't put the plus 0 for the y-intercept, right? Same thing here. If they don't put the a here, because there's no number, we assume it's a 1. So a lot of parallels, right? It's just a different number. So you can say why? Because it fits the format, fits the form, in the form of a b to the x. Now, there's a little personal choice you have to make. You can write this with a dot, or you can write it with the parentheses. You'll see it written both ways. They're equivalent. If you have really good writing, it doesn't matter. But if your writing's not so good and you do something like this, like the dot's so small it can't be, seen, and you're not really good at being very, complete with your work, then that could be a problem. And if that's the case, I'd say use parentheses, because if you put parentheses, it's very clear what the b value is, and you're not, well, I was in a big hurry, and I know, it's there. Can you see it? Especially, people grading your AP test. You don't want to do all this work and then, well, they couldn't tell what you're trying to say, so they marked it wrong. So put parentheses if you're anywhere close to being ambiguous. If not, then you can use either. All right, next, is this in the right format? AB to the x? And then you would say? No, because? Yeah, variable is not the exponent, right? It has to be to the x power. This is not to the x power, it's to the -3 power. This would be a rational function, by the way. This would be equivalent to 4 over x to the third, and then we'd have vertical asymptotes. Right? What about here? We got a number to the x power. Even though it's -x, that's fine. Like, yes, that's fine. Same thing in the form of AB to the x. Okay. Still in the right format. And what about the last one? Is this in the correct form? And then you say? No, because? Yeah, there's no variable. There's no variable. There's no x. So all letters are not created alike. That's a variable. E is a number. That's 2.73. This is a number. If you do 3 times 4 to the e, you'll just get a number as an answer. There's no graph or anything. If you did graph it, it'd just be one single point because it's just a number. It's like saying 2 pi plus 1. Right? It'd be 7.28. It's just a number. There's no graph here. So now we know or recalled here what a exponential has and does not have. Okay. So next, let's just plug in some values and just double check we're not making any order operation problems or mistakes. So go ahead and plug in, it says 2, plug in 2 for f of x here. And get your answer. And then on B, also plug in 1/3 and get your answer. And it should be done without a calculator. Basic calculations, we do not need a calculator here. Okay. And what'd you get for A? 162. Good. And what did we get for B? Still working? So what is 8 to the 1/3 power? What's another way of writing 8 to the 1/3 power? How about cube root of 8? So fraction powers are roots. So 1/2 power is the square root. So we have -1.5 times 2, so we get -10. And common mistakes here, sometimes you'll see an 18 to the 3rd power because they're doing multiplying before exponents, and sometimes you'll see, oh, that's 6 times 9 because every now and then we get a 3rd to the 3rd power. Someone says it's 9, like 3 times 3 instead of 3 to the 3rd. So just be careful, it's neither one of those. Right? So it's actually 6 times 27. There we go. Okay, so just reviewing. Just reviewing right now. And here we go. Let's see. We need 2 values, right, to find a function. So g of x equals AB to the x power. So we need to know, do we know where this graph is starting? What's the y-intercept? And you say? Yeah, either right here or right here. Either way, it says it started with 3. And do we know what the growth or decay factor is? Output value of G doubles times 2. So that's just finding the equation of an exponential. Still need 2 pieces of information, where we're starting, how much is it growing or decaying. And then, of course, we can fill this out by doubling it. So double, and then double, double, and double, 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 and double, 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 double. Yeah. And now we're all hungry. All right. Okay. Hopefully it's going well. Like I said, just a lot of Algebra 2 review. See if you can find the equations for both of these. All right, they got to be in the format f of x equals ab to the x. All right. So what is the y-intercept on the first one, on A? So we got 3. What's the ratio? 2. Okay. About the second one, what's the y-intercept? And what's the ratio? All right. Yay. Okay. So it's just looking, scanning, finding the right values. Checking, okay, we're multiplying by 2, multiplying by 2. Here we're multiplying by 1/2, multiplying by 1/2. Okay. All right, let's keep on going. Okay. So here we're going to do just a little sketch, but because we have a positive number that is greater than 1, is this a growth or decay factor? Is this growth? So all that goes hand in hand right here. The fact that we got greater than 1. Right? And we have a y-intercept of 3. So just to sketch, we'll know that that's 0, 3. And we already know the behavior looks something like this. It approaches an asymptote this direction, and it approaches infinity that direction for growth. Right, so to the right here, going towards positive infinity. Right, we're going to go up to positive infinity. And to the left, as we go towards here, we're going to get closer and closer to 0. And our domain and range will not change for exponentials, which is very cool. So the domain, it can go left or right forever. All right, we can have super small positive fractions, or we can have super big numbers. And our range, right, we can't go below the x-axis, so it'll never go down here. It gets close to 0, but never quite equal to on the left. And then on the right-hand side, we're going to go up forever. There we go. Of course, it's going to be very similar, but not the same. So if we have 1/2, it's going to be a what? Is that how you spell it? DK? All right. We have a 5. We have 0, 5. but it's going to decay, so that means it's going this way. So what is different about the rest of these the limits? Are they the same limits? Yeah, so here on the left, that's when it's going to infinity, not the right. So now as we approach negative infinity, that's where it's approach infinity. And then on the right-hand side, that's where it's approaching 0. So you notice the limits compared to the first one have switched. What about the domain? Is the domain same or is that different? Same, all right. What about the range? Same or different? Same. What about the asymptote? Same or different? Same. Same. Okay. All right. So it sounds like we're catching on or remembering all this. Okay, last problem. So this is just comparing a linear with an exponential. Exponentials always grow faster, so when you graph both of these down below side by side, you expect eventually for the exponential curve to be above the straight line. So we're just going to do this by the numbers. So we have two companies, and they're opening up locations or buildings, could be like a Starbucks or Cane's or whatever. They're just expanding, right? And one's expanding arithmetically, so it's growing by 10 each year. And the other one's growing geometrically or exponentially, so it's going to go up by 40% each year, right? And that's why it's a 0.4. So let's look at the differences and how they compare. So we have the first one is big tech, so B of 0. It's just going to be 25 plus 10 plus 0 times 0. So we get 25 locations. That's what it says we're starting with, 25 locations. And then the other company, C of 0, is going to be 25 times 1. I'm going to put together the 1 and the 0.4 to 1.4, which means 100% of the buildings we already have plus 40% more than we already have. Okay, and that's to the 0 power. But of course, this also says we're starting with 25 locations, so when you plug in 0, 1.4 to the 0 is just 1, and then we get 25 times 1. So they're both starting with the same number of buildings or restaurants or whatever it is. However, if we start growing big tech, we know it goes up by 10 restaurants per year. So year 2 would be 35. And we could plug it in and show it, but it's not necessary. This is a very, very basic calculation. So by year 4, we're going to have 65 stores or locations. What about the right-hand side? So it's 2.5 times 1.4 to the 1. You need a calculator, figure that out, and do that for each one. Yes? That's a good question. When I'm 64. All right, so what do we get for the first year? 2.5 times, 25, sorry. 25 times 1.4 is? Well, 35. So even after 1 year, they're both the same. What about after 2 years? Multiply that answer, 35 times 1.4. What do you get? 49, thank you. And one more time after that, what do we get? What is it? 6? No, 6, 8. And lastly, 68 times 1.4? 96. Now, should I have the decimals here? 49.1. Should I have decimals here or no? No, because we're talking about locations, buildings. We can't have decimals of those. So honestly, that's probably the biggest difference on these FRQs of that on your answers. It's not really the little mathematical parts and did you multiply by 1.4 correctly. It's understanding the problem in context. So knowing you can't have fractions of locations. No one's ever opened half a Starbucks, right? And just common sensely knowing that from the very beginning and not putting it there. So when you go to graph it, we have whole numbers only. So go down here and plot all the points. For the linear, it's a good idea just to plot the first one and the last one. So if you go 0, 25, and then 4, 65. 0, 25, and then 4, 65. Like that. And then you just draw a line. Or not erase, draw a line. Connecting them. Okay. And then everything else, since it is linear, should automatically line up. You're not really trying to make the dots connect. You draw the line first and then go from there. Okay. Now for the exponential, the two first points are the same, 25 and 35. And that's something they asked right here in part B. So both at x equals 0 and 1, they have the same value, 25 and 35. But then when we get to 3, it jumps to 49. Three is 49. Why is this wrong? This is wrong. Something's off. Something's off. Something's off. What's off? Double check this. 465, right? There we go. Try it one more time. So here and here are the same. And then 2. 2 is 49. Okay, yeah. Slightly above. There we go. 3 is 68. Not 67. And then 4 is 96. And we could continue this one more. It says, what's the maximum locations for 5 years? So they're asking what happens at 5 years. So what happens if we go to 5 years here? So we can do that two ways. We can go back up here and just multiply 96 times 1.4 one more time. Right? And that will give us, I think, about 134. So for here, we get 134. And then from here, of course, it'll just be 75. 10 more, which is what we get right here. Now, when you're drawing this curve, it goes like this, and it gets here. It'll actually go lower below. The curve will be actually lower at first, and then it goes above. So a good question here would be, well, when is this function less than this function? They said, well, when is c of x less than b of x? Right? That'd be, where is this graph below this graph? You could say, oh, from 0 to 1. Okay. So we have, b of 5 was 75. C of 5 was 134. what is the domain and range for this problem, for the context of this problem? Because it's no longer negative infinity, right? You can't have negative infinity years. So how would you adjust the domain and range to fit the context of the problem? So what's the lowest domain or the lowest number of years according to this model? 0, I heard it. Now, technically, we could say we can go on forever. However, that would mean we can go infinite years into the future. So I would say infinity with an asterisk, because you really, in reality or real life, we're not going to be using this one model for ever and ever and ever. We might use this for a 5-year plan or something like that, but it would technically probably not go forever for the rest of the days. And same thing for range, right? What's the fewest number of stores or locations we started off with? 25. And theoretically, how many stores can we have total? Yeah, I guess this graph, both of these can go this way forever, but once again with an asterisk, because at some point you can't have 100 million billion locations, right? So there is some cap here. We don't know what it is, but once we get in supply and demand and markets, then we could actually come up with a better answer here. But for now, we'll say it just keeps on going. Okay, so a nice little review, Algebra 2, and good little talk about everything else. So let's get started on the homework. Got a little bit of time.